Hello, everyone. Thanks again to Mantra for hosting this event, and thanks, Alan, for giving me this opportunity to talk. Today I'm going to talk about Rust in data science, and I'm going to mainly focus on polars and exploring, different frameworks on, how to, what is the state of data science in Rust. But first, just a little bit about myself. My name is Luciano, passionate about data and programming in general. I love learning new things and sharing knowledge with others. That's why I really like to participate at these events and meeting new people. Currently, I'm working for a consultancy company in aviation. So I work with a variety of clients such as airlines, airports, and working with data and providing insights to these clients. And I also like to do some open sourcing and exploring Rust in general as a tool. Mainly, I'm a Python developer, but I don't know if you've noticed in the past few months, the Python ecosystem is getting oxidized a little bit with a lot of Rust-based tools, such as polars, in fact. And that's what really made me more curious about Rust and learning. Still try to learn every day, but so today I'm going to talk mainly about polars. There's going to be some code examples as well, so feel free to follow along if you want on the GitHub repository. So just wait if you have to scan. Okay, cool, perfect. And yeah, so everything is available. Of course, feel free to spot any bugs if there's any. Hopefully none, but I cannot guarantee this. So you may want to use the code, or you may not want to use it anyway. So here we go. So before talking about polars, I wanted to talk a bit more about the state of data science in Rust in general. So as you may know, Rust has a series of different crates and different ecosystems where it's trying to show its presence. But there is still not a lot of, let's say, modern crates on data science itself. There are some. One of them is being Arrow, which is the Rust implementation of Apache Arrow. I'm not sure if you can see the image properly, but if you've downloaded the slides, you can see it. So there's Arrow, there's polars, and these are really the two major crates that I would recommend if you want to start manipulating some data in Rust itself. So Arrow, it's actually a multiple language toolbox. And it's actually, so it's implemented, you have it in Python, you have it in Rust and C++ and other languages. What Arrow does, it gives a definition on where and how to store data in memory. So essentially, it's almost like a protocol, we could say. And we'll see later on in this slide why Arrow is important. And then there's also polars. So polars is a DataFrame library. So basically what it does, it offers a series of optimization out of the box. So it has multi-threading, vectorization, and it has its own query engine, basically. And it's written purely in Rust. So some exciting feature about polars, well, it is compatible with Apache Arrow. So again, Arrow is, let's say, the common framework that tells us how the data can be stored. And polars use some of the features that Arrow exposes, for example, native columnar data storage. So essentially the data, instead of being represented, let's say row by row, it's represented column by column. And we'll see why this is a really exciting feature and why it's, let's say, a feature that allows polars to be this fast. It has a lazy API, which you might think it might be, it's not very common to have lazy API these days. And, we'll see later on why it's so exciting. Multi-threaded out of the box. So what polars does is it makes your code, let's say, more efficient. So you as a polars user, you just define a series of instructions, and polars query engine will basically optimize your queries and make the code more efficient in general. So you don't really have to think about how to parallelize certain process or how to multi-thread your program. Polars will do that for you internally. It has a chip, so I'm not going to talk about, let's say, the internals on how polars work in Rust, but what you need to know is that it has a very cheap copy on write structure. So what we usually do as a data scientist, you would like to manipulate data in many ways, and you will often reference columns many times, or you may have to redo certain actions over and over. So the infrastructure that Polars provide is that you don't really have to care a lot about, let's say, cloning an object in Polars or re-referencing multiple columns, because the Polars code itself will make it, let's say, easy to have multiple references and execute your code multiple times. And then last but not least, it has a good query plan optimization. So when we talk about query plan optimization, we mainly talk about two main features. One of it is predicate push down. So essentially, let's say we have a car database and we want to filter. So what we do is we load this database and we want to filter, let's say, all cars manufactured by Toyota. And later on in the code, we also want to filter all cars that are red. So what predicate push down is, it looks at, let's say, the final output, and it looks at what are the most important filters that you have applied. And it will try to put these filters as soon as you read the file. So essentially, it will push down the filters down to the first execution of the script itself. So basically, when you have a file, it will put those filters, and it will try to basically, as soon as the file is read, there will be all the data that you don't need will not stay in memory, right? So we don't really want to load everything into memory. So, and this oftentimes will work with some more, like, let's say, intelligent data formats such as Parquet, where it exposes the metadata of the data itself. So you don't necessarily need to read all the file to infer the schema of the data. And the other level of optimization is projection pushdown. What projection pushdown does is it looks at how many columns you are actually utilizing and how many columns you're not utilizing. So in our database, if we just want to select the manufacturer column and the, let's say, car color column, it knows that, okay, these are the two main columns that we're going to use, and therefore all the other columns don't need to be read and don't need to be stored somewhere in memory. So these are the important features that Polars have. Of course, there's more, but let's have a look more about what is a data frame, right? So a data frame essentially is a table. So it's constructed with columns and rows, as you can see here. And these columns are basically also called series, commonly called series. And they have a constraint. So the constraint is that every column has to have its own data type. So for example, here for the timestamp column, there's only one data type. I'm not expecting here to see any strings. And as you can see here, every column has to have the same shape as well. So one thing that one of the constraint that is not present is that every column can be nullable, right? So there might be empty data in each row. And so this is the way that, the data frame is the core object that you're going to use in Polars. And so the way it works is that it uses internally the Arrow implementation. So what Arrow does, it has a columnar storage, as I said before. So every value is stored in a column. And what it does, it offers a series of advantages. One of them is better compression. Since we already know what is the data type inside of the column, we don't really need to know, we don't have to calculate, infer the schema on our own. Everything can be compressed into its own data allocation. For example, if we have a column that's an I32, we can already, the Polars already know how much memory to allocate for that column specifically. It offers better cache because you can access each columns more efficiently, since every data is already organized, let's say, evenly, thanks to the Arrow implementation. It reduces I/O because we already know which columns to take. You don't have to scan for every row of the entire file, the entirety of the file, for example. And it allows something that's called, single instruction, multiple data operations. Essentially, when you use Polars API, you almost never have to iterate over the data, over the columns. What you can do is you can apply a function to a specific column or to a series of columns, and this function will then apply, let's say, what you intend to do to every items of the row themselves. So you don't really have to, again, iterate over, you don't have to do a for loop and iterate over every row. You can just think about a column like if it was an expression, essentially. And of course, it's more memory efficient because we can just scan different columns and we don't have to scan the whole file and the whole rows. So this is an idea on how Arrow, let's say, outlines the data. So usually in a normal buffer, you will have like on a row-wise perception. So basically, every row is allocated in each slot. And you can see already where the trouble comes is that if I only need certain rows in the normal buffer on the left side, I will have to still scan. Sorry, if I need to check certain columns, I will still have to scan every row. So I will have, if I only need the session ID, I will have to scan every row and take the first element of that row. But what Arrow does is that it organizes the data into the different columns. So if I only need session ID, it's already slotted in, and Polars can grab it very quickly. So Polars has different APIs. It has two major APIs, the eager one and the lazy API. So the eager one is, let's say, the most easy to understand because it just does everything step by step. So at first it loads the data. Then let's say you want to filter the data. So you will filter then the data, and everything. It's basically, so the advantage of the eager API is that you always have the results of each intermediary step. So you want to access, let's say, from this step to this step, you already have you can already access the output of it. But you can already see where things starts to fail is that, well, if my database or if my file is very large, then you actually have to load everything into memory. And then, yes, maybe you're going to filter certain rows, but it will still stay everything into memory up until the final output of your result. But the cool thing that Polars exposes is a lazy API. So if I'm not mistaken, in the Polars documentation, the lazy API is what is recommended. So if you're starting up with Polars, you may as well start up with the lazy API first, because I would say it's the most simpler to use. And it's definitely the easiest and the simplest API in general, because what you do in the lazy evaluation is that what Polars does, it will use all the different instructions of your code and optimize them, and then later on it will execute it. So if let's say in the output, we end up having only 10 rows, then there's not so much data that will be loaded into memory at once. So, and the cool thing is that since Polars will know all the instructions that you've put into your code, is able then to optimize it. But this optimization is not possible if in your analysis, in your ETL, you're doing everything step by step. And by the way, I understand that this is already a lot of information, so feel free also to interrupt me. But there's going to be maybe some time later on for questions, but feel free to interrupt me at any point. So yeah, you can see there's lazy API and the eager API. But enough about talking. Let's see more about some code, and let's put some code action. So what I did here, I downloaded a publicly available database about buildings in Hong Kong. I didn't want to take any sample data or like any data that has fewer rows. I wanted to have a substantial amount of data so that I can showcase what Polars is capable to do. And yeah, I was just thinking buildings in Hong Kong it's a good database because we are here. And we can all relate to whenever we see outside all the buildings and stuff. So I think it must be fun to work with it. So again, the code is available in the GitHub repository, and it will, if you execute some examples, it will already download the data for you. But if not, there's also a link on where to download it. So the data that we're working with it today is a GeoJSON. So for those, is anyone here aware with what a GeoJSON here? Have you? Okay, cool. So anyway, for the rest of us, so the GeoJSON is basically a JSON file, but it follows a specific schema. So that's the schema that on the screen that you see. So it has a first few lines is basically the metadata of the GeoJSON object. So we can see, okay, what type of object is this? It's a feature collection. We have the name. And then this is basically the coordinate reference for the different shapes. And so here we have different features. And these features is really what the data that we are interested in. So the top height of each building, we have the building name, we have the number of ground stories, record creation date. So we have a series of fields for each building in Hong Kong, at least what is publicly available. And then we have a geometry field, and this will represent every point that you need to, let's say, draw an outline of a building. So it will be lat and long coordinates. So what you may have noticed already that this is a very nested type of data. So how can we actually, we can actually read this data with polars, and we can unnest every different field so that we can start working with it. So this GeoJSON specifically has 400,000 features. So you can think of 400,000 buildings themselves. So this is just a small snippet on what working with polars might look like. I do have some helper functions here that I've created. Everything is available. You can look into it, but I'm not going to really go too deep into it. So essentially, load data. It's downloading the file for us in this path that we specified. Unnest data frame. It's basically unnesting every field that we have here, so that we have at the end of the day we will have a ready-to-use data frame for our data transformation. But essentially, what you can see here is that we are importing the prelude of polars, and as you can expect, that's the best way to start working with polars, is that we import all the tools that are available, and then out of this tool that polars exposes are different readers and writers, and this is really where the API distinction starts. Basically, you can have eager readers that will give you a eager data frame, and you have lazy readers. Those will, instead of reading everything into memory, will just, let's say, maybe scan for the schema of the file, and then it will allow you to continue with the lazy frame object, which is basically part of the lazy API. And by the way, before I start compiling some code, you must know that polars does have a lot of features. And this is so that the developers thought that, okay, it might as well be nice for developers to have their own features and reduce the size of the binary, because if you try to put everything, so if you try to access all features all at once, you might have a big binary. So for example, for the JSON reader, you need to have the JSON feature, and the whole lazy API as well comes also in its own feature. So make sure that you select the feature you need before you start working with polars itself. But here, essentially, what you can see, I'm selecting a column. So that's the eager way to select a column, is you basically use the column method and you call it by name. And the thing about the eager API is that everything can be a result, a polars result. So we have to make sure that we handle those results accordingly. And as you can see here, I'm actually printing it. So the cool thing about polars is that it implements debug for most of its objects. So you can actually see, the data itself. And, with the eager API, the cool thing, you can see every intermediary steps of your data transformation. So that's, really helpful. And yeah, one cool thing we can do is we can create new columns. So in this case, I want to know, let's say, how many records were created each year. So what I can do is I select the record creation date. I use the .stir. So what this does is it gives me access to the string namespace. So essentially, what polars will usually do, it will scan for the schema, or it will infer the schema of the file. And so if there is a data, of course, JSON's, it's all strings, so it will scan for the schema. And if there is a string that looks a numeral, it will becomes an integer, or it will becomes a float. In this case, sometimes, you can specify the options on how to parse the schema in the reader parameters itself, but sometimes it will just, scan it and create it infer it as a string. So we can access the string namespace here, and what it allows us to do is access it as if it was a string itself. And here I have different methods. So I want to cast this string as a datetime, and I'm specifying the actual string format for that specific datetime. There's other parameters here that we can ignore. And essentially here, I just want to pick the year. So as soon as I've converted it as a datetime, then I have all the datetime properties and fields. So here I'm just extrapolating the year parameter. So we went from a string to a datetime to essentially a I32 in just these lines of code. And what I can do finally is I assign a name to this column, and essentially our data frame will have a new column in it. Of course, you might think, okay, well, actually, I could have just taken the 4 first character of the string and get the year, but I just wanted to make it nice and and proper, so that we can have see the different transformation and different tools that access us. So we can also print the columns here, and I will compile the script later on, but you can imagine we're going to have the different years. And essentially what we can do now is we can group by the year and count how many object IDs we have for each year. And then I want to have the output presented in a descending order. And that will be the representation of the final data frame. Essentially, the whole code is actually here for us. And again, what we can do is we can do cargo run example, and I'll call it eager. I'm using the release flag here simply because, I don't expect to do any debug, but also the release, Polars built on with the release flag is so much faster. So, also to see the actual performance of Polars. So now executing the code, it should be running fine. But yeah, so essentially what we expect to see, here we go. So we have printed quite some stuff. So what we've printed here is actually the entire data frame. So that's the representation, a debug representation of the data frame itself. As you can see, it has been truncated by default. This is because, you expect to be working with, quite a lot of data. So you have the availability to work with quite a lot of data. So every time you print something, you don't necessarily need to see everything. Of course, the best way to see everything would be to export it into a CSV or another date format. But yeah, you can see here it has parsed everything properly into the different columns. And we also have a struct type. So the cool thing is that you can have structs inside each row, and you can access the field of its struct as well. So we'll see this later on in action. What I did here as well is I have printed the creation year column. So you can see that's how a series is represented. So it's an I32, and that's basically almost like an array, if you want to say. And yeah, that's the final aggregation that I did. So we have the vast majority of records was created in 2005. So probably that's where the database was started being created. And then later on, we have probably around 5,000 records. And then in 2022, we had 1,100 records or so. So that's one thing. So as you can see, any questions so far? So that's a very basic transformation, but that's really, the bread and butter of what you can do with Polars in the Eager API. So here we go. So if there's no question, let's move on with the lazy API. So just as a reminder, the lazy API, what it does, it just collects different instructions that you're going to put to your data itself. So I want to filter, I want to create new columns, I want to do aggregations. And after I give all the instructions, there was going to be a query plan that's going to be optimized and then executed. And with all the benefits of the optimization in Polars. So we have predicate pushdown and projection pushdown as well. Of course, as you can see in the code before, I haven't really thought about multi-threading, parallelization, and all of that because Polars handle all of this for us in the lazy API. We're going to see later on. And yeah, so you can see most of the benefits here. I don't really want to go into details, but that's what we did before, but with the lazy API. And what you can see already is that the lazy API is quite similar to the Eager one, with some exceptions. When we access, for example, a namespace, we don't really going to have a result because essentially the data is not loaded yet. So the lazy API is way more flexible, but we just have to make sure that the only times we're going to expect a result is when we actually collect the data. So we can build our plan, create our own expressions and columns, and we're only going to see later on if everything actually works. So that's one of the caveats of using the lazy API, is that you have to make sure that what you're referencing actually exists in your data. Otherwise, you're going to have a panic. And the other cool thing is that the column here becomes an expression. So you no longer need to access the data frame itself. You can start building your expressions, and then at a later stage, you can add those expressions into your lazy frame in that case. So before I mentioned that we also have the different outlines of the buildings, but what if I actually want to start working with, let's say, the distance between each building, or if I want to have a distribution around a certain area? Well, having all this data is not really helpful for me. All I need is actually the center of each building to calculate the XY coordinates of the building itself. And we can do this in Polars and in Rust using other tools, other crates. So now I'm using the geo crate that will allow me to calculate the centroid, so the center of a polygon. So what I did here, I created this function here that accepts, let's say, a nested vector of f64, and will return me just lon and latitude of the building itself. And the cool thing is now I can plug this into my existing polars code. So let's have a look. Here we go. So actually, before doing that, I also have a small lazy example. So here with this macro, we can create a data frame on the go. So instead of having a file to load, we can properly create a data frame. So here I'm exposing the columns and the values inside each row. As you can see, for example, column A is just integers. Column B has some nullables, so it has none, so nothing in the first row, and then some strings, and column C is purely strings. And here I can reference it to a new column here. So this will be column D, and it will be column A plus literally the value 10. So it will be 11, 12, 13. And the cool thing is that I don't need to work into this constraint. I actually can create my own expression here. Let's say column D. And yes, let's put it here. Here we go. So as you can see, the cool thing about the lazy API is that you can do this, you can create your own expression literally everywhere. You can create a function that returns an expression. You can create another function that accepts an expression and do something else. And as soon as the query plan doesn't spot any issue for you, everything is fine. You can just press collect, and all will be good. Then here I have another transformation with column C, accessing the string namespace. As you can see, column C is here, and I want it to be in uppercase, and I call it upper C. So let's have a look. Eager, and this is called basic lazy. Yeah, it actually needs to compile it again. Okay, cool. So as you can see, that's the new data frame. Actually, what I could have done is show you before and after, right? So let's have a look. Print ln. So I'm just going to use this. And what you might have seen is that we are first creating a eager data frame. And the cool thing is that there's a .lazy for every data frame. So this is allow you to go back and forth to the different APIs. So you can do everything into memory first. And then once you're happy, you say, okay, now we start doing things lazily. So you can, let's say, build more complex expression in the lazy API. And personally, I think the lazy API is much simpler. So you may as well start with the lazy API anyway. So now just adding the before and after. And let me save it. Okay. So yeah, so as you can see, we have A, B, C here. And here we go. Then we have upper C. So yeah, that's about this simple lazy API. Let's go back to our example. So we can calculate the centroid. And essentially, we are accessing the geometry column. So if we go back up, let's have a look. There we go. The geometry column is a struct, and it actually tells us, different information. So there are two fields in this struct. Probably the first one is the object name, let's say, and then the other one is actually the data itself. So what we can do is, the other one is called coordinates anyway. So what we can do is we access the struct name field here, and we can get the field by name or also by index. And in this case, it's coordinates. So coordinates will be this, let's say, representation here. And this is yet a list. So we access the list namespace, and then we can grab the element of that list that we need. Since this is actually a nested list, we need the first element. It can go on forever, but I realized later on that this data structure is quite nested, so the code can be a bit spaghettified. But yeah, essentially at the end of the day, what we do is we have a vector of coordinates that we will feed into our built-in, let's say, native Rust expression. But of course, the best thing would be to actually access the lazy API first and only go through these black box functions only when the Rust API, the Polars API doesn't give you access to. So if you do simple arithmetic, or let's say you're using string manipulation, you can do all of this without really having to go outside of Polars, right? And then another thing we can do, so now that we have a centroid that I'm calling it coords, so the coordinates x and y, and actually, fun fact, I'm just using another struct with the x, y field, what we can do is we can calculate the distance. So we're using the hover-sign function to calculate the distance between 2 points. So I can also plug this into our script. And essentially, now we can, let's say, get Soho House coordinates, lat and lon, and we can have the distance of every building based on where we are right now. And here I've prepared a little report. So let's say, for example, floor area distribution in square meters. So what I did is, this is the best way actually to use the Polars API, is to use the function that returns an expression. So here I'm getting the column name, the column by name. So I'll just use the call function. Then, I can create different buckets. So this allows me to create buckets of equal size. So I can specify the column name and the size of the bucket. So here I'm saying I want a bucket that goes, for each step, it goes by 1,000. So the first step will be 0 to 1,000, then 1,000 to 2,000, and so on. So then I will have a new column called cross floor area bucket. And then I can count on how many IDs there are for each bucket. And I want to sort it in descending order. Later on, the second, let's say, insight I want to get is what is the tallest building? So what are the top 10 tallest building in this data frame? So what I'm doing is I'm getting the column top height, and I say it's greater than this value, 100 meters in that case. And I also want to add, and you can see here how the query optimization is going to work, is that I'm using different filters at different, let's say, step of the code. But what Polars is going to do is going to apply these together as soon as the file is being read. So this is, let's say, a native way to use Polars itself. So instead of using Rust functions, I just go ahead with the native API, which is actually the recommended way. So greater than, I don't have to create a native Rust function to compare the numbers in the column. I can just use the greater, the GT method in this case. And here, you can see the projection pushdown. So I only actually need to see these two columns instead of seeing all columns of the database. And I can actually drop empty data. I can drop the columns that have null data. So because, of course, I don't need it for this analysis. Later on, what we can see is building height by record creation. So I guess you get the deal. We are grouping by creation year that we have created before. I also have another example of building density. That's a more complex one, where we have all the buildings that are present, like all the buildings by distance, and the distance is how far it is from Soho House. So maybe it's gonna be clearer when I actually show it to you. So let's have a look. So this is report. Is it going to build it again? Here you go. So here we have nice tables. Again, this is just the very beginning. Ultimately, you want to export this table somewhere, and what Polars does, it simply allows you to write these into a database, write these into S3, into a JSON as well. So it can convert this table representation into a JSON, and you can write it in multiple files as well. So here we have our first KPI. So floor air, the count of buildings by each bucket that we have created. Building names, so the highest building. We have the average height and the building count for every year, creation year. Later on, we have building density. So we can see that most of the buildings here closer to us, within 1 kilometer, are around 64 meters. And that's the average floor area. As we go further away from Soho House, we'll have smaller average floor area per building. So that's really basically about Polars itself. So what we've seen is that it gives us an optimizer, blazing fast query execution. Oh, that's a bit too small. Native multi-threading. So you've seen in my code there was no mention of threading and processes and parallelization, because everything gets done already by Polars. And then, of course, what I like to do with Polars is that it's relatively production ready, in terms of that it really it really checks that every column is accessed properly, and every type inside the column is also accessed properly. So I cannot use a string method with a column that was inferred as a date, for example. And of course, cross-platform, built native in Rust, so you get all the amazing features that Rust gives you. And then, why not plug it into your back end? So imagine you have a REST API that, gives you a report on demand. And some people might think, okay, well, I can already do this. Why should I use Polars? Well, I think one of the advantage with Polars is that it already gives you a series of tools to read multiple file formats. So I think most of the time, if you're working with files, I think Polars is the best way, it's the best tool to use. Of course, if you have like ephemeral data, or if you have data already in memory, then you might as well use something else. But if you're working with CSV or even Excel files, Polars is the tool to use. Yeah, as I said before, you have Parquet CSV JSON, excellent for ETL because Polars provides you a lot of tools for, let's say, string manipulation. It provides a lot of tools for date time. So for example, you have multiple timestamps and you want to group them by the specific frequency. You can group them by month, you can group them by hours and so on. So all of this comes in built in with the caveat that you have to use the proper feature and build it in your binary. And yeah, it's a familiar data frame. If you work with other data frame libraries before, you might be familiar with using series and columns. And yeah, so I really like Polars itself. It has many features as you can see, and it also has a Python. I think Polars is most commonly known as a Python tool. But the cool thing about the Python implementation is that it's just some, let's say, front end to the core Rust. So I've seen that Python code can still perform quite good compared to the native Rust code. And actually, I would say sometimes writing it in Python will, we all know Python is less, let's say, constrained. So you might end up creating more complex expression in Python, and those expressions will then be converted into Rust itself. So, have a go to see, both documentations and both implementation of Polars itself. So yeah, that's about it. Please let me know if you have any question. I understand it's quite a lot to digest, but yeah. Cool. Thanks. Process. There's still more stuff in the repository itself. Oh, there's already a PR. That's great. Cool. Hopefully, it's not like a spelling error or something like that. Cool. But yeah, so that's really about it. I think maybe like if I can add one thing about it is that the main barrier to Polars in Rust itself is, let's say, it's not super well documented in terms of, I would say the Python API is much more like much better documented than the Rust one. So sometimes even while working on this presentation, I was looking at, okay, how would I have done it in Python? And then it's like, okay, let me see if there's if I can access any method with that same name in Rust. But the cool thing is that, whenever you're trying to deploy something in Python on production, you always have to think about dependencies and maybe you want to Dockerize it and so on. But with Rust, you have your own binary. You can compile it for multiple platforms and build tools around it. So, and also, building Polars in Rust also is also nice because it gives you access to every Rust crate. So if you're already using a Rust tool, then you can easily combine it with Polars. So yeah.